Module 5, TCP/IP for Automation and Instrumentation. Networking that scales beyond one plant. At this stage in your journey, something subtle but important happens. Up to now, networks have felt local. A bus, a ring, a star, a panel, a plant floor. TCP/IP is where networking stops being local and starts being systemic. This is the moment where automation networks stop thinking like wiring diagrams and start thinking like infrastructure. And the fastest way to make sense of TCP/IP without drowning in IT theory is to compare it directly to the OSI model you already understand. TCP/IP versus OSI, fewer layers, same responsibilities. Let me say this clearly up front. TCP/IP is not simpler because it's weaker. It's simpler because it's opinionated. Where OSI describes everything that could exist, TCP/IP focuses on what must exist to move data reliably across scale. That's why TCP/IP collapses 7 OSI layers into 4 functional layers. Same engineering problems. The 4 TCP/IP layers, what they really mean to you. TCP/IP organizes networking into 1. Network interface layer, 2. Internet layer, 3. Transport layer, 4. Application layer. Instead of memorizing names, I want you to map them to things you actually touch as an automation engineer. Network interface layer, how bits hit the wire. This layer combines what OSI splits into physical plus data link. Cables, NICs, Ethernet frames, MAC addresses. This is where Ethernet lives, switches operate, frames are formed and checked. If a link light is off, you're here. If CRC errors appear, you're here. The tutorial explicitly points out that this layer represents OSI's lowest layers and is responsible for framing and local delivery. This is the layer OST comfortable with, because it's tangible. Internet layer, getting packets from here to there. This is where IP lives, not Ethernet frames, packets. The internet layer doesn't care about cables, it cares about addresses and routing. Its job is brutally simple. Open quote, take this packet and get it to the destination network. Close quote. This is where IP addressing exists, subnets matter, routers make decisions. The tutorial highlights that this layer performs packet transfer between hosts and is operated by the Internet Protocol itself. If you've ever asked, is this device, do I need a gateway, why can't I ping it? You were debugging the internet layer. Transport layer, do you want speed or certainty? This is where TCP and UDP live and where automation decisions start to matter. The transport layer is responsible for end-to-end data integrity, regardless of how many networks are crossed. Here's the key distinction. UDP fast, lightweight, no guarantees. TCP slower, heavier, acknowledged, ordered, retransmitted. This is where engineers implicitly choose between latency versus reliability, fresh data versus correct data. And this choice shows up everywhere in automation. Cyclic I/O, diagnostics, configuration tools, historian uploads. The wire didn't change. The expectation did. Application layer, where meaning finally appears. This is where TCP/IP stops being plumbing and starts being useful. The application layer is where FTP moves files, TFTP loads firmware, Telnet enables remote access, custom automation protocols live. This is the layer humans and control logic actually interact with. Importantly, what the application does, only how it rides on the lower layers. That openness is why TCP/IP scales from one PLC to entire enterprises without changing its core structure. Mapping TCP/IP to OSI, the mental shortcut. Here's the fast mapping you should keep in your head. TCP/IP network interface, OSI physical plus data link. TCP/IP internet layer, OSI network. TCP/IP transport layer, OSI transport. TCP/IP application layer, OSI session presentations application. Same responsibilities, less ceremony. That compression is intentional, and it's why TCP/IP survived while OSI remained mostly conceptual. Why automation engineers should care. TCP/IP matters because it allows automation systems to scale across plants, connect to IT systems, share data globally, survive vendor boundaries. But it also introduces assumptions, best effort routing, shared infrastructure, non-deterministic paths. Understanding the layers lets you place blame correctly when things go wrong. If you don't know the layer, you reboot everything. If you know the layer, you fix the problem. The bridge forward. Up to now, we've been mapping structure. Next comes behavior. Because once packets can travel anywhere, the real question becomes, how do we keep automation traffic reliable when the network spans the world? That's where TCP versus UDP stops being an IT debate and becomes an engineering decision. IP, ARP, ICMP, what ping actually proves and what it doesn't. This is one of the most misunderstood moments in automation troubleshooting. You're on site, a device isn't talking, someone types ping, it replies, and everyone relaxes. That relief is often misplaced, because ping proves far less than people think. And understanding why requires knowing how IP, ARP, and ICMP quietly work together underneath. IP, logical addressing, not physical reality. Let's start with IP, because everything else hangs off it. An IP address is not a physical location, it's a logical identifier. IP's job is brutally simple. Open quote, get this packet from one host to another, possibly across many networks. Close quote. It does not care about cable type, switch brand, MAC addresses. Whether the destination is a PLC or a laptop IP only knows. Source IP, destination IP, routing rules. That's why two devices can share the same Ethernet cable, but never communicate if their IP logic disagrees. This is why subnet masks and gateways matter so much in plants. They decide who is considered local and who must be routed. ARP, the translator Ethernet, can't live without. Now comes the layer almost no one thinks about. ARP. Ethernet does not understand IP addresses. Ethernet understands MAC addresses, so when an IP packet needs to be sent on an Ethernet network, one critical question must be answered first. Open quote, what MAC address corresponds to this IP address? Close quote, that translation is ARP, Address Resolution Protocol. Why happens? 1. A device wants to send an IP packet. 2. It checks its ARP. 3. If no entry exists, it broadcasts. Open quote, who has IP x.xx? Close quote. 4. The correct device replies with its MAC. 5. The sender caches this mapping and proceeds on. This happens silently, constantly, and invisibly, until it doesn't. Why ARP is a common hidden failure point. If ARP fails, IP packets cannot be framed, Ethernet has no destination, communication silently stops. Common ARP-related field problems include duplicate IP addresses, stale RP tables after device replacement, incorrect subnet assumptions, layer 2 isolation issues. From the outside, it looks like, open quote, the network is fine, but nothing works. Close quote. ARP is the reason Ethernet feels magical when it works and maddening when it doesn't. ICMP, what ping really uses. Now let's finally talk about ping. Ping is not a general network test. It is a very specific test using ICMP, Internet Control Message Protocol. ICMP exists to provide diagnostic feedback, test reachability. When you ping a device, you are asking, open quote, can you receive an ICMP echo request and send me an echo reply? Close quote. That's it. Nothing more. What ping actually proves, if ping succeeds, it proves only this. The IP address exists, routing to it works, ARP resolution succeeded, the device is powered and responding, ICMP is allowed. That's already a lot, but it's not everything. What ping does not prove, this is the critical part. Ping does not prove that TCP ports are open, that UDP traffic is flowing, that the application is running, that the PLC program is healthy, that the protocol stack above ICMP works. A PLC can reply to ping and still reject every Modbus TCP Ethernet iProfinet connection. Ping is reachability, not usability. Why engineers overtrust ping? Because ping is fast, visual, binary. Works doesn't work. And because in many cases fixing IP or ARP does fix the problem, so engineers start treating ping as a universal truth test. It isn't, it's a layered truth test. The layered interpretation you should use when you ping successfully, here's the correct mental translation. Open quote, the internet layer is alive, ARP at the network interface layer is working, and the device is minimally responsive. Close quote, nothing more, nothing less. If ping fails, you debug, power, IP addressing, subnets, ARP, routing. If ping succeeds but the system still fails, you move up the stack, not sideways. The takeaway that saves time in plants, ping is not a comfort blanket. It's a scalpel. Use it to isolate layers, not to declare victory. Once you truly understand what ping proves, you stop arguing in control rooms and start diagnosing like an engineer. And now that we've nailed IP identity and reachability, the next question becomes unavoidable. Even if packets can reach the destination, how do we ensure they arrive correctly, in order, and on time? That's where TCP and UDP finally step into the spotlight. TCP versus UDP, reliability versus speeding. This is the decision automation engineers make constantly, often without realizing it. Every time data moves over TCP/IP, one quiet question is being answered. Open quote, do I care more about getting the data correct or getting it now? Close quote. That question is the entire difference between TCP and UDP. And it's not an IT debate, it's a control philosophy. TCP. I need this to be right. TCP was designed with one obsession: certainty. Its job is to make an unreliable network behave like a reliable pipe. To do that, TCP enforces discipline. Every segment is acknowledged, lost data is retransmitted, data arrives in order, congestion is actively managed. The tutorial describes TCP as the heart of the TCP/IP suite, providing reliable, protected transfer of data between applications not free. TCP introduces handshakes, buffers, retries, variable latency. TCP does not promise when data will arrive. It promises that it will arrive intact. Where TCP makes absolute sense in automation, TCP is the right choice when wrong data is worse than late data. Think about configuration downloads, firmware updates, recipe transfers, historian uploads, asset management tools, engineering workstations talking to PLCs. If a byte is missing, duplicated, or corrupted, the entire operation is compromised. TCP says, open quote, slow down, let's be sure, close quote. And for these use cases, that caution is not just acceptable, it's mandatory. UDP, fresh data beats perfect data. UDP takes the opposite stance. No handshake, no acknowledgements, no retransmissions, no ordering guarantees. UDP simply sends data and moves on. The tutorial explains UDP as a minimal overhead protocol offering basic addressing and checksums, but no delivery guarantees. At first glance, but in control systems, it often isn't, because sometimes old correct data is worse than new imperfect data. Why UDP exists at all in industrial systems. Consider a fast-changing process variable. Speed, position, flow, temperature, trending rapidly. If one update is lost but the next arrives on time, the control loop stays stable. But if the network waits to retransmit old data, the controller reacts to the past. That's dangerous. UDP favors low latency, predictable timing, continuous freshness. It accepts loss as a fact of life and designs around it. Where UDP is the right engineering choice. UDP shines when data is cyclic, updates are frequent, timing matters more than completeness. Typical examples: cyclic I/O updates, real-time measurements, motion control data streams, multicast status distribution. In these cases, the system logic already expects constant updates, occasional loss, no retries. UDP aligns with that expectation. The mistake engineers make early on: many engineers assume, open quote, reliable network equals TCP everywhere, close quote. That instinct comes from IT. In automation, it backfires. TCP can introduce jitter, bursty delays, head-of-line blocking, all of which destabilize time-sensitive behavior. UDP looks crude, but it's often more honest about time. The control-oriented mental model. Here's the way I want you to think about it. TCP protects correctness, UDP protects timeliness. Neither is better. They answer different risk questions. Ask yourself, can my system tolerate missing data? Can it tolerate delayed data? The answer tells you which protocol belongs there. Why this trade-off defines industrial networking. Modern industrial Ethernet protocols don't blindly choose TCP or UDP. They mix them. TCP for configuration, diagnostic supervision, UDP for cyclic I/O and real-time exchange. Same wire, same IP network, different expectations. And that's the real lesson. TCP/IP doesn't force one behavior. It gives you tools. Your job as an automation engineer is to choose the one that matches process reality, not network comfort. Once you internalize this, protocol choices stop feeling mysterious and start feeling inevitable. And that's exactly where good engineering lives. Application layer, FTP, TFTP, Telnet, where networking actually touches engineering work. Up to now, everything we discussed lived in the background. Frames, packets, routing, transport behavior. Important, but invisible. The application layer is where networking finally becomes useful to automation engineers. This is where configuration changes, diagnostics happen, and real work gets done. And the reason protocols like FTP, TFTP, and Telnet still matter, even in modern plants, is because they solve three very practical problems: moving files, loading devices, talking to machines directly. The application layer, meaning not transport. The TCP/IP model is very intentional here. Lower layers answer, can data get there? Will it survive the journey? The application layer answers, open quote, What are we actually doing with this data? Close quote. The tutorial makes this explicit. This is the layer where the end user interacts with the host, using specific protocols designed for specific tasks. Live here more than they realize. FTP, when correctness matters more than speed. FTP, File Transfer Protocol, exists for one core reason. Open quote, move files correctly. Close quote. FTP runs on TCP, which means files arrive intact, bytes arrive in order, corruption is detected and corrected. That reliability is why FTP is used for program backups, configuration exports, firmware packages, historical data transfers. When you download a PLC program or upload a configuration archive, one missing byte can brick a device. FTP accepts delay to guarantee correctness. That's not overhead, that's protection. TFTP, when simplicity beats sophistication. TFTP, Trivial File Transfer Protocol, looks like FTP's lightweight cousin, and that's exactly what it is. TFTP strips everything down. No authentication, minimal commands, runs over UDP, very small overhead. Why would anyone, industrial devices, have limited resources, need simple boot time file loading, must start before full services are available? That's why TFTP is commonly used for firmware flashing, bootloader operations, device startup configuration. TFTP assumes, open quote, the network is local, controlled, and trusted, close quote. It trades security and robustness for simplicity and predictability. In isolated control networks, that trade-off often makes sense. Telnet, raw access, raw truth. Telnet is one of the oldest application protocols and still one of the most honest. Telnet provides remote terminal access, text-based command interaction, direct visibility into device behavior. There's no GUI polish, no abstraction, ice. That's why Telnet remains valuable for diagnostics, debugging, verifying services, low-level configuration checks. If you've ever typed a command into a device and seen an immediate response, Telnet was likely involved. It doesn't hide mistakes. It doesn't protect you from yourself. And that's exactly why engineers trust it. Why these protocols still matter in automation. Modern systems often wrap these functions inside tools and GUIs, but underneath, FTP still moves files, TFTP still boots devices, Telnet-style sessions still drive diagnostics. Knowing what's actually happening underneath saves you when tools fail. When a configuration download stalls, you don't blame the PLC. You ask, is FTP reachable? Is the port open? Is TCP behaving? When a device won't boot, you don't reboot blindly. You ask, is TFTP responding? Is the file accessible? Is the network reachable at startup? This layer turns networking from mystery into leverage. The mental model that ties it together. Here's how I want you to think about the application layer. FTP protects correctness. TFTP enables simplicity. Telnet exposes truth. They exist because automation needs reliable file movement, lightweight device loading, direct human-machine interaction. And while newer, more secure protocols exist today, these classics still define how industrial systems are configured, diagnosed, and recovered. Once you understand them conceptually, tools stop feeling magical, and failures stop feeling random. At this point, you've climbed the full TCP/IP stack, from copper to commands. From here on, everything else is industrial personality layered on top of these fundamentals. And that's exactly where advanced industrial Ethernet protocols begin.